Hello and welcome to another episode of the Software Defined Networking course. In this lecture, we are going to study how the SDN works. At the beginning of this course, we start our journey by studying the SDN architecture. We explored three different layers of the architecture in details. These layers are the data plane, control plane, and then the application plane. Now we are going to see how actually these layers work together in order to achieve the objectives of the SDN. So here is a brief roadmap for today's presentation. We are going to start this lecture with the fundamental characteristics of SDN. And there are going to be 5 characteristics, and they are quite familiar to us now. For example, the characteristics that we are going to explore in a moment are plane separation, a simplified device vision, a centralized control, network automation and virtualization in openness. After that, we will have to move to the SDN operation, how it actually works. And then the structure of the SDN device and SDN controller and some applications of the SDN. Finally, we will see some other implementation of the SDN architecture. So first, let us see the fundamental characteristics of the SDN. The first fundamental characteristic of the SDN is known as plane separation. Separation of the forwarding and control planes. Forwarding functionality including the logic and the tables for choosing how to deal with the incoming packets, like which are going to be based on for example MAC addresses, IP addresses or virtual LAN IDs, and these things reside in the forwarding plane. The fundamental actions that are performed by the forwarding plane are like whether the packet is going to be forwarded, or it is going to be dropped, or maybe it is going to be consumed or replicated. So all these are the actions that are actually performed by the forwarding plane. For basic forwarding, the device or the switch actually determines the correct output port, and that is done by performing a lookup in the table. So a packet, an incoming packet, may be dropped because buffer is full, or due to some specific filtering results from quality of service, a packet may be dropped. Special case packets that require processing by the control or management planes are consumed and passed to the appropriate plane. So finally, a special case of forwarding is like the multicast, where the incoming packet must be replicated before forwarding the various copies out there. So actually these are the actions performed on the incoming packet. A packet may be forwarded, maybe it is dropped, maybe it is replicated, and the reasons I shared with you. So to shed more light on the control separation, actually the logic and algorithms that are used to program the forwarding plane, they actually reside in the control plane. Remember, we have two planes. Let me show you. We have the data plane and we have the control plane. So the logic and algorithm that are actually used to program this forwarding plane, they resides inside the control plane. And many of these protocols and algorithms, they actually require the global knowledge or global view of the network. So actually the control plane determines how the forwarding tables and logic in the data plane should be programmed or configured, because they are like dummy devices just forwarding the packets based on the information that they receive from the controller. So the actual brain is the controller. Since in a traditional network each device has its own control plane, the primary task of that control plane is to run routing or switching protocols so that all the distributed forwarding tables on the devices throughput the network stay synchronized with one another. But in SDN, the control plane is moved of the switching devices. Now it is moved and it becomes a centralized controller. Okay, so that is the first characteristics, that actually we separate the control plane from the data plane. In simple word, that is the first characteristic. The second characteristic is this simple device and centralized control is the third one. Simple device is simple. Okay, you can say that the switches concept is now simplified, and these simplified switches are actually controlled by a centralized system from the control plane. So instead of hundreds of thousands of lines of complicated control plane software running on the device and allowing the device to behave autonomously, that software is now moved from the device and it is placed in the centralized controller. Okay, this software based controller is now the boss, because it now manages the network based on the higher level policies. So you can say that the controller actually provides primitive instructions to these simplified devices, the switches. And when appropriate, in order to allow it, actually allow these simple devices to make fast decision about how to deal with the incoming packets, whether the packet need to be forwarded, whether the packet need to be discarded, whether the packet need to be replicated, and things like that. So these are the two more characteristics, that the switches devices are now become simple and we have a centralized control on top of them which actually manages the network based devices. Our next characteristic is automation and virtualization. So SDN can be derived precisely from the abstraction of distributed state, forwarding, and configuration. The distributed state abstraction provides the programmer a global view of the network, and it actually shields the programmer from the realities of a network that is actually comprised of many machines. Abstraction is there. So the forwarding abstraction actually allows the programmer to specify the necessary forwarding behaviors without any knowledge of the vendor specific hardware. And also we have the configuration abstraction, which is sometimes called the specification abstraction as well. And it must be able to express the desired goal of the overall network without getting lost in the details of how the physical network will implement those goals. Actually, we have studied these types of abstraction in our previous lecture, week number 6. These three types of abstraction. So the point that we need to focus here is that the centralized software-based controller in the SDN actually provides an open interface to the controller. and that interface will allow the controller for automated control of the network. This is the main point. And you know the northbound and the southbound interfaces, they are often used to distinguish whether the interface is to the application or whether the interface is to the devices. And as we know that an example of a southbound API is the OpenFlow interface that the controller uses to program the network devices. So we are now going to study how the SDN works. So it is important how the OpenFlow interface is used by the controller. So OpenFlow interface is used by the controller to program the network devices. And also the controller offers another API, that is the Northbound API, and it actually allows the software applications to be plugged into the controller. These applications can quickly and dynamically make network changes. We are studying network automation now from the applications point of view. So the application running on top of the controller, they can quickly and dynamically make network changes as the need arises. The Northbound API of the controller actually provide an abstraction of the network devices and also the network topology. Another characteristic of the SDN is openness. What does it mean? It means that the SDN interfaces or APIs should remain standard. They should remain well documented and not proprietary. The APIs that are defined should give software sufficient control to experiment with and to control various control plane options. So we have to keep open both the interfaces, the northbound and the southbound, to the SDN controller. And this openness will allow for researcher into new and innovative methods of network operation. They can check different solutions if the APIs are available openly. You can perform easily experiment and you can test new ideas because the things are open. And it also this openness encourages several projects throughout the world which are related to the SDN design and implementation and things like that. So openness is a brilliant feature. And also the open interfaces, it will permit equipment from different vendor to interoperate. That is another beauty of the open interfaces, and this normally produces a competitive environment between the network equipment manufacturers. So these are some fundamental characteristics of the SDN. Next is the SDN operation, how actually things work. This architecture is pretty much familiar to us now, okay, because we have the 3 layers here. This is a conceptual level architecture, and from this architecture we are going to understand the operation of the basic components of the SDN. And what are those components? Those components are the SDN devices, and also the second component is the controller and the applications. The easiest way to understand how SDN operate is to follow a bottom-up approach, starting with the SDN devices. As we know that the SDN devices, which are also known as the switches, they contain forwarding functionalities. You can see we have a device here and it has forwarding functionalities, and these forwarding functionalities are there to decide what to do with each incoming packet. Beside from the forwarding functionality, this device also have the data. and this data drives those forwarding decisions. The data itself is actually represented by the flows. So we have the forwarding functionalities, we have the data in the form of the flows. And these flows are defined by the controller. As you can see here in the controller, we have the data and forwarding as well. So a flow is actually a set of packets transferred from one network endpoint to another endpoint. The endpoints may be defined like IP addresses, port numbers, virtual LAN, MAC, etc. One set of rules describe the actions that the device should take for all packets belonging to that particular flow. So a flow is another point is that it is unidirectional, in that packet flowing between the same two endpoints in the opposite direction could constitute a separate flow. Okay, so we also know that we have the flow tables that actually resides on these network devices. Beside from forwarding functions, data in the form of flows, we have the flow tables which actually resides on these devices, and that flow table contain a series of flow entries and also the actions that need to be performed when a packet matching that flow arrives at the device. For example, when the SDN device receives a packet, it consults its flow table in order to search for a match. If the SDN device finds a match, it takes appropriate action. What to do with the packet, like forward the packet or discard the packet or replicate the packet. But if it does not find a match in the flow table, the switch can either do other actions like it's time to drop the packet or maybe pass it to another controller. Okay. Now this is about the devices. So we have the forwarding functions, the data in the form of flows and flow tables. If we give attention to the controller now, the SDN controller is actually responsible for many things, like it has to abstract the network of the SDN devices that it controls, and presenting an abstraction of these network resources to the applications, the SDN applications that are running above the controller. So the controller actually allows the SDN applications to define flows on these devices and also to help the applications to respond to the packets which are forwarded to the controller by the SDN devices. So in this figure, we see that on the right hand side of the controller, it maintains a view, a global view of the network, of the entire network that it controls. This global view will permit it to calculate optimal forwarding solutions for the whole network. As one single controller can control a large number of network devices, these calculations are normally performed on a high performance machine. Like you have to install the controller on a high performance server. And we have the applications. SDN applications are built on top of the controller. These applications should not be confused with the application layer that is defined in the OSI model or the TCP/IP model. Okay, they are not the application layer applications. So what they are? The SDN application are actually the network applications. And we also have an interfaces. So these applications talk to the controller with the help of an interface. There is a word that we use here, and that is the proactive flows. The SDN application interfaces with the controller actually uses proactive flows on the devices. Proactive flows are established by the application. Typically, the application will set these flows when the application start up, and the flow will persist until some configuration change is made. Like you have a flow of data from the application to the controller and to the devices, and this flow will exist until some configuration setting has been changed. And this kind of proactive flow is known as static flow. We also have another type of flow where the controller actually decide to modify a flow based on the traffic load currently being driven through a network device. In addition to the flow defined proactively by the application, some flows are defined in response to a packet forwarded to the controller, and upon receipt of incoming packet that have been forwarded to the controller, the SDN application will instruct the controller as to how to respond to the packet, and if appropriate will establish new flows on the device in order to allow that device to respond locally the next time it see a packet belonging to that flow. And these flows are known as reactive. So proactive flows handled by application and reactive flows handled by the controller in coordination or collaboration with the applications. And in this way, by using the reactive flow, it is now possible to write software applications which implement forwarding, routing, multi-path propagation, and access control functions, among others. So this was the basic operation of the SDN. We have three layers. At the bottom, we have the devices, and the device, SDN device, has components like the forwarding functions and the data in the form of the flows. And a flow is actually a set of packet that is transferred from one endpoint to another endpoint. And also we have flow tables which have different entries, and each incoming flow is compared with the entries in the table. If a match is found, the flow is forwarded. If a match is not found, then other actions are taken. And then these flows are actually received from the controller, and a controller provide a global view of the network. Okay, and on top of the controller we have the applications, and these applications are not the application layer applications, these are actually the network layer applications. And those applications, actually the flows are defined by the applications, and those flows are known as the passive or the proactive flows, or the static flows, but sometime the controller may change the flow or the configuration by its own by taking instructions from the application. In that case, those type of flows are known as the reactive flows. After studying the SDN operation, let us see SDN devices. So again, we are going to focus at the bottom layer, as we just saw that the SDN device has two components: forwarding flow, and also it has the flow table. So let us see them. You can see it here. The device or the switch is actually composed of an API, and the API is used for communication with the controller. You see, on top we have the controller. To communicate with the controller, we need an API, and the common API is the OpenFlow. We also have an abstraction layer, and also a packet processing function. Here we have a packet processing function. Here we are going to consider two things, two types of devices, software and hardware. Software is like virtualization and hardware the actual device. So in case of a virtual switch, this packet processing function is packet processing software. Actually, this is a software piece, a piece of software. While in case of the physical switch, this packet processing function is actually hard coded, embodied in the hardware for packet processing logic, as you can see here. The abstraction layer in the hardware or even in the software, they actually embodied one or more flow tables. Now we know what is the concept of flow table. The packet processing logic actually consists of the mechanisms to take action based on the results of evaluating incoming packets, as we just saw. So the switch has to consult the flow table. When a match is found, the incoming packet is processed locally. Okay. But when no match is found, the packet may be copied to the controller for further processing. What to do with the packet? In case of a hardware switch, these mechanisms are implemented by the specialized hardware. In case of software switch, is somewhat simpler. The functionalities are simpler because they are programmable as compared to the hardware switch. So this is actually the device which contains three things: an API to communicate with the controller, abstraction layer, and the packet processing. When a packet receives, packet processing is activated. It will find a match in the flow table. If a match is there, the packet will be forwarded. If there is no match, then it will consult the controller what to do with the packet. Now let us see in detail what is actually this flow tables or the information within the flow tables. Actually, flow tables are fundamental, you can say, data structures in the SDN devices. And these flow tables allow the device to evaluate the incoming packets and take the appropriate actions. Packets have traditionally been received by networking devices and evaluated based on certain fields. Like a packet has certain fields. So depending on that evaluation, actions are taken. What are those actions? Maybe the action is to forward the packet to a specific port. Maybe the action is to drop the packet, or maybe the action is to broadcast, flood the packet on all ports. Or it could be any other things as well. Flow tables consist of a number of flow entries, sometimes prioritized. Each of the entry typically consists of, for example, two components: the match field and the action need to be performed. Match field are used to compare the incoming packets. An incoming packet is compared against the match field, and when a match is selected, actions are performed. And actions are the instructions that the network device should perform if an incoming packet matches the field. So this is the role of the flow tables in forwarding the packets. What else? Okay. Next we have the SDN controller. The SDN controller actually maintains, as we just saw, a global view of the whole network. It also implements policy decisions. It controls the SDN devices. It provides a southbound API and a northbound API. Southbound API for communication with the devices, and northbound API for communication with the applications. The controller actually implements policy decisions, and those policy decisions are actually related to routing, forwarding, redirecting, load balancings, and things like that. Controllers often they come with their own set of common application modules. You can see in this figure, like a learning switch, like a router, like a basic firewall, load balancing, and things like that. These are really, if you focus on them, they are like the SDN application, but they are often bundled within the controller. Remember from the last lecture, we have part of the applications that are actually embedded in the SDN controller. So it seems like the SDN applications, but they are actually bundled within the controller. So controller may come with their own set of common application modules, and some of them are mentioned in this figure. Let us see them in details. The figure can also show the modules that provide core functionalities of the controller. It also contains a Northbound API and the modules there, and also the Southbound API is used here. An example is given, which is OpenFlow, and here we have plenty of options available: REST, Python, Java based API, etc. So here we have the OpenFlow. I mentioned earlier that we lack standardization for the controller to application interface. Okay. And different organizations have developed different standards, like the REST API, which is the most common one, Python and Java, etc. So let us see the core modules of this SDN controller. The controller actually, as we know, that it abstracts the details of the devices, and it will allow the applications above them to communicate with those devices without knowing the details of those devices. So every controller provides core functionalities, and core features in the controller will include, like for example, we have end user device discovery, like the discovery of end user devices, whether it is a laptop, a desktop, a printer, mobile device, PDA, etc. And also another functionality is network device discovery. So DISCO stands for discovery, and the discovery could be of end user devices or network device. And network devices are like switches, router, access point, etc. We also have module for topology management, like it will maintain information about the interconnection details of the network devices to each other, what kind of topology they have. Okay. We also have another core module that is the flows management, and for that it will maintain a database of the flows being managed by the controller, and it will perform all necessary coordination with the devices to ensure synchronization of the device flow entries with that database. Another core function of the controller are so we have seen that is the device discovery of the device, discovery of the topology, and also it has like the tracking, flow management, and also the device management, and statistic as well, statistic tracking. These common core functionalities are implemented in the controllers, and they are internal to the controller. These modules need to maintain local databases which will contain like the current topologies and statistics of the network. The controller also tracks the topology by learning of the existing of the switches, which are the SDN switches, and also the end user devices, and tracking the connectivity between them. So these are some of the modules which actually are implemented inside the SDN controller. Beside from these core modules, we also have interfaces. For the applications, a key function provided by this SDN controller is the API for accessing the network. In some cases, this Northbound API is like low-level interface, providing access to the network devices in a common and consistent way. In this case, that application is aware of the individual devices, but these devices are shielded from the user. In other instances, the controller may provide high-level APIs that provide an abstraction of the network itself. Like in some cases, it will provide an abstraction of the devices, low-level interface, while in other cases, it will hide the details of the whole network itself, so that the application developer can develop applications without knowing, without concern about the individual devices, and also without concern of the network as a whole. So let us see another closer look of the interfaces to have an idea how the controller interfaces with the application, the northbound interfaces. So the controllers, actually we have the application, you can see on top of the controller, this is actually the Northbound API, and we have three options available here. So it communicates with the application. Okay, so in some cases this API, it could be low level interface, or in other cases it could be high level interface. But in both the cases, the controller actually informs the applications of different events. You see, from this side we are communicating the events. Okay, from the controller to the applications, the communication is in the form of the events. What is event? Event may pertain to an individual packet that has been received by the controller. Okay, or some state change in the network topology, like a link goes down, change in topology. So that is an event. On the other side, applications use different methods, you see, from the application to the controller. And these methods are used to affect the operation of the network based on the event that it received. These methods could be like invoked in response to a received event, and it may result in a received packet that is being dropped, or that is being modified, or that is being forwarded, or the addition or deletion of modification of a flow, etc. So you can see actually application is instructing the controller, and then the controller takes the necessary actions. Okay. Okay. One more thing about the SDN controller is that currently more than 20 SDN controllers are available in the market. You can see we have different APIs here, which means we have different controllers available there, and there is still no standard for the Northbound API. So that is why sometime this Northbound API is known as NBI, which is Northbound Interface. From implementation point of view, there are a number of implementation of the SDN controller available on the market. They both include Open SDN controller and Commercial SDN controller. Some of them we studied in our previous lecture as well. Open source SDN controllers come in many forms, like from basic C language controller, from Java based controller like Beacon, and also REST or even Python based controller. And the open source controller are like the Open Daylight, which we have studied. Another one is Open Network Operating System, ONOS, that we also studied, and it's gaining attraction from the researchers as well. So different implementations are available, different SDN controllers are available in the market. But the basic functionality is that actually it has to communicate with the applications in the form of events, and then the applications inform appropriate actions in the form of methods. Okay, now we studied the devices. We open the devices and we see how it works. We open the controller and see the different components and APIs. Now let us see the applications and how it works. SDN applications. The first point is that these applications actually run on top of the SDN controller, and they actually interfacing to the network with the help of the controller Northbound Api. These applications are responsible for managing the flow entries that are programmed on the network devices. This is something very important. The communication is started at the application layer, but the actions are taken at the device level. That is called the programmable networks. You are able to program the devices at the application level. And the beauty is that all the details are actually hidden. Abstraction is there. SDN applications are actually responsible for managing the flow entries that are programmed on the network devices with the help of the controller, because the controller has to manage the flows. Okay, so the Northbound API is actually allowing the applications to do several things, like they would be able to configure the flows to route packets through the best path between two endpoints. They are able to balance traffic loads across multiple paths. They are able to react to change in the network topologies like link failure, addition of new devices, etc. And also they are able to redirect traffic for the purposes of inspection, authentication, and other functions like security related tasks. To other modules, they have the capability to transfer the to reroute the traffic for these purposes to other modules. Here in this figure, you can actually see, this is actually the same figure. I have placed it again here in order to focus on the applications now. So you can see that we have some standard applications like graphical user interface. This graphical user interface is used for managing the controller. If you want to set or configure a controller, you will have to use the graphical user interface. And we also have a learning switch, a routing application, and other things. Beside from that, additional logic is necessary to react to newly seen MAC addresses, and also to update the forwarding table in the devices. Actually, this additional logic is embodied in the learning switch. Graphical user interface is used to configure the controller. A learning switch is used to react to the newly seen MAC addresses, and also it is used to update the forwarding table in the SDN devices. And this logic has been implemented in this learning switch application. One of the strength of this SDN architecture is in the fact that switching devices can be controlled by these family of applications. Okay, So we have a devices at the infrastructure layer, but we are controlling those devices from this layer, application layer. And there are going to be other applications as well, like load balancer, like firewall, like security, like privacy, like trust related, like load balancer, etc. and so on. So the list goes and go on and go on. Now one question, what are the responsibilities of these applications? So the general responsibility of an SDN application is to perform whatever function for which it was designed. And what are those functions? It could be load balancing, it could be firewalling, or some other operation. They have to perform it. So how it works, how things works, when the controller is on, it will initialize the devices and it will report the network topology to the application. Now the application will spend most of its processing time responding to the events. You see, we have events that were received by the applications from the controller. So most of the time the applications are going to receive different events, and then they will respond to those events. Application behavior is actually driven by events, and those events are coming from the controller. The application actually affects the network by responding to the events. As we saw, they respond to the events with the message, with the methods. So the SDN applications actually registered as listener for certain events, and the controller will invoke the application's callback methods whenever such an event occurs. So some example of events handled by the SDN application are like end user device discovery, network device discovery, incoming packet, etc. Now, another question is that how these applications respond to the event. So there are many ways in which an SDN application can respond to the events that it receives from the SDN controller. There are going to be simple responses such as downloading a set of default flow entries to a newly discovered device. And these default or sometimes static flows typically are the same for every class of discovered network devices, and hence little processing is required by the application. However, there are some cases in which the complex responses are required, and they will require static information that they gather from some other sources apart from the controller. And this can result in variable responses depending on that state information. But these are some details, high level details, so we are not going into dig further into these areas. But the main concept to understand here is that actually the application have certain responsibilities, and they have to communicate with the SDN controller with the help of these APIs in the form of events and methods. Okay. Next, let us study alternative methods for the SDN. The SDN architecture that we have studied in this course until now, they are called Open SDN. And this Open SDN has a greater support in the research community, and also amongst the network operator, and also the large data centers such as Google and Yahoo. They have strong support for this Open SDN. However, there are other proposed methods of accomplishing at least some of the goals of the SDN. And these methods are generally associated with a single networking vendor, or maybe a group of vendors. Up till now, two alternative categories of SDN implementations have been proposed. One of them is called SDN via APIs, and the second one is via hypervisor. Let us see them one by one. SDN via with the help of APIs. Consider that the basic concept of SDN is to move control functionality from devices to a centralized controller. Then this can be accomplished in other ways than the open flow centric approach, which is coupled to the open SDN. We can achieve this through other way. Okay, so the key functional improvements by using the SDN approach are programmability and a centralized control. Programmability will provide the opportunity for the applications to be written in order to automate the process and to provide a level of dynamic control. On the other side, the centralized control will provide the ability for applications running on a controller or independently to have views of the entire network. We have seen these two properties. SDN allow us for programmability, and it also gives us a centralized control or a centralized common view of the whole network, of the entire network. So in this figure, actually we have a number of levels at which APIs can be provided for SDN applications. Like we have the APIs at the policy level, we have the APIs at the controller level, and we have the APIs at the policy at the device level. So let us see them and discuss them one by one. First, let us focus on the starting from the bottom one. Let us first see the device APIs. Okay, so in SDN through device API, the strategy is to provide a richer set of control points on the devices so that centrally located software can manipulate those devices and provide the intelligent and predictable behavior that is expected in the SDN controller network. What you can see in the figure is that a set of centralized applications. We have a set of centralized applications, and these applications are communicating with these devices. These are the devices. Okay, and this communication is through this API, and this API is actually the device API, and as I just mentioned, they are going to be proprietary. So vendor will actually provide an enhanced level of API on their devices. This is the API on the devices, and the applications are communicating with these devices with the help of this API. If you give attention to this figure, you will see a difference from the previous approach. And the difference is that in this case, this controller is actually optional. In the previous cases, applications communicate with the devices through the controller. However, in this case, the applications can communicate with the devices without this controller or with this controller. This is because even when the controller is present in this paradigm, it adds little or no value to the communication between the application and the devices because it happens to the API. Indeed, the application may sometimes communicate with the devices directly without using a controller at all. Since the early days of the commercial internet, it has been possible to set configuration parameters on devices using methods like CLI and SNMP, Simple Network Management Protocol. While these mechanisms have long been available, they can be cumbersome and difficult to maintain. Okay, so note that in this figure, the communication to the devices using these APIs. Okay, we are not using controller, and also we are not using the open flow. So the communication is directly through the APIs. And this is another way of implementing SDN with the help of APIs. But the API is between the application and the devices. Our next setup is the control APIs. Okay, so here if you compare these two figures, there is a little difference. We still have the devices, we still have the API, we still have the application, but here we have the controller. Here the controller was optional, but here we have the controller mandatory. So in order to promote programmability from a centralized location, SDN through control level API can provide a platform from which we can build SDN applications. And the solutions that we are going to provide by using this architecture, they actually utilize the set of APIs provided by the controller. And these APIs are open and available for application developers. As we know that there is no standard for the northbound APIs, for the northbound interfaces, applications written from for one controller set of API may not run on a different controller. So in this figure, you can see that the SDN through controller API is possible. As you can see, this model is not different from our previous model. This one seems like the same thing. Okay, it seems like the same thing. So what is the difference between this model, which is the SDN Open SDN, and that model that is the SDN via controller API? So what is the difference? The fundamental difference come in the nature of the southbound API that the controller uses. In case of this Open SDN, the southbound API is the open flow, while in case of this SDN controller API, the southbound API or protocol will consist of one or more legacy protocol that are being repurposed to provide SDN-like functionalities. Remember, SDN with the help of API. Here we are not using open interfaces, we are using proprietary interfaces. So there we used open flow, but here we have to use proprietary interfaces. So the difference is in the southbound API. Okay, one goal of implementing API at the controller level is to provide a level of abstraction between the devices and the application, like abstracting details of each specific device and each specific protocol, and making it possible for the applications to interact with the controller at a high level. In this case, in this scenario, the applications benefit from the work done by the controller and is able to read information about these nodes and links from the controller without having to perform the actual devices and host discovery and topology. Our third SDN via API is the policy level API. These two are the same things. The difference is only that here we are dealing with policies now. So this is another approach, and it provides a level of APIs which actually resides at a layer above the controller. You see, we have an API above the controller, but we also have the policies here. These APIs are actually created at a level of abstraction such that they address policies instead of individual devices or network capabilities. They are focusing on the policies, and these APIs come in different flavors and may be directed at different target domains, but they try to address network configuration from declarative perspective rather than imperative. What is declarative and imperative? Imperative actually mean systems and APIs, they actually require the user to input exactly how to do a particular task. While on the other side, the declarative system and APIs, they request the user to input exactly what is to be accomplished. It is the responsibility of the system to determine how to do it. So in this figure, we can see that SDN through API, and notice the policy layer which is running on top of the controller, and it providing functionalities and a level of abstraction which shields the SDN applications from the underlying details of interacting with a specific device. Okay, these policy based API solutions are gaining traction in recent years. Many researchers are working on this layer to define different policies for such type of networks. Policies related to management, policies related to forwarding, related to security, related to functionalities of the devices and things like that. So these things are related with the policies. The second approach is SDN through hypervisor, and that is by using the concept of overlay network virtualization, and it is an innovative alternative SDN method which is known as hypervisor based overlay network. Under this concept, the current physical network is left as it is. We do not mesh up with this physical network. We do not mesh up with these devices at the physical network or at the physical layer. Their configuration remains unchanged. But above this network, however, the hypervisor-based virtualized networks are created. The systems at the edge of the network, they actually interact with these virtual networks. And these virtual networks will hide the details of the physical network from the devices that actually connect to the overlays. And such an arrangement is shown in this figure, where we can see that the virtualized network overlying the physical network infrastructure, and the SDN applications making use of these overlay network resources. They are giving access to the virtualized networks and ports which are abstract in nature and do not need necessarily relate directly to their physical counterparts below this network. So conceptually, the virtual network traffic runs above the physical network infrastructure, and the hypervisors, their role is very critical. Actually, they have to inject traffic into the virtual networks, and actually they have to receive traffic from it as well. So the traffic of the virtual network is passed through those physical devices, but the endpoints are unaware of the details of the physical topology, how routing occurs, or other basic network functions they are unaware of. Since these virtual networks exist above the physical infrastructure, they can be controlled entirely by the devices at the very edge of the network. In data centers, for example, these would typically be the hypervisors of the virtual machines that are running on each server. Okay, the mechanism that make this possible is tunneling, but let us shed some light on the tunneling. Actually, the concept is encapsulation. Because we have different types of packets, the physical network packets are different from the virtual one. So we need encapsulation. We need to encapsulate the packets. When a packet enters the edge of the virtual network at the source, the networking devices, maybe the hypervisor, will take the packet in its entirety and will encapsulate it within another frame. This is shown here. We have a payload, and then we encapsulate this payload into another packet, into another frame. So when a packet enters to the edge, the hypervisor will take the packet and will encapsulate it into another frame. Now the hypervisor then take this encapsulated packet, and based on the information programmed by the controller, it will send it towards the destination. At the destination, the packet will be decapsulated and it will be forwarded to the destination host. As the encapsulated packet is sent across the physical network, it is being sent from one source device to another and then so on. So consequently, the IP addresses are those of the source and destination, but internally inside the network virtualization, we have to encapsulate the packet. This approach mandates that a centralized controller be in charge of making sure that there is always a mapping from actual destination host to the destination hypervisor, because at the virtual level the communication is like between the hypervisors, which acts like a host. So encapsulation play an important role in this type of setup. So in summary, SDN through hypervisor based overlay network is well suited to environment where there is large number of servers like data centers and they are already running it at a full-fledged, and the concept of virtualization has already been implemented in the data centers. Nevertheless, these overlay networks, they do not solve all the problems that can be addressed by the open SDN solution. Why? Because it does not address existing issues within the physical infrastructure, which still remain manual configuration and maintenance. We do not change anything at the physical level. So in the introduction to this, we said that overlays the current physical network is left. We do not change anything here. So with the networking devices and their configuration remaining unchanged, under this assumption, hypervisor-based overlay do not directly address the desire to open up the network devices. And that is one of the requirements of the SDN, that we have to open the devices, we have to separate the control plane from the data plane. But here those things does not happen. Okay, so now this was the last slide, and we studied two different methods by using which we can implement SDN. Okay, so thank you so much for attending the lecture. We will have a discussion in the online session. Take care and goodbye.